Welcome to Empowered Learning. This video will be the first video in a series on hyperbolic functions. In this first video in the series, we will establish what a basic hyperbolic function is, or what the hyperbolic functions are, rather. We will see how we can model our basic hyperbolic functions to be something similar to the basic trigonometric functions that we are used to seeing, but we're going to see how they're different as well. So after we do that, we will do things like establish what are the derivatives of our basic hyperbolic functions, what are our basic antiderivatives of our basic hyperbolic functions, and then we'll close out this first video with some examples on how to take hyperbolic expressions and simplify them. All right, so let's get started. So the first thing that I want to talk about is how we actually model a hyperbolic function, and how those types of functions are very similar to how we model trigonometric functions. So if you look at figure 1a, then what figure 1a is showing you here is what the first quadrant of the unit circle would look like, okay? So of course we have our point 1, 0 here, have our point 0, 1 here. And notice that I've shaded in this sector area, okay? Now, we know that in figure 1c, this is what the whole entire unit circle looks like. And we know that with the unit circle, we have a radius of 1. So this r that you see right here in figure 1a is actually a value of 1. So if we look at that and we say, all right, we remember that the sector area formula is just 1/2 times the radius squared times theta. And of course, theta would be in radians since we're using, an algebraic expression to calculate it. And noting that r is 1, we see that the sector area is essentially just whatever the angle measure is divided by 2. Now, what I want to note here is that if we remember the arc length formula, which is S is equal to R times theta, and if R is equal to 1, then what that means here is that theta is actually mimicking our arc length. So another way of looking at this sector area here is that if the sector area is theta divided by 2, then the sector area, that value is actually half of whatever the arc length is from this point A to this point P, okay? Now, where all this kind of ties in with hyperbolic functions is that here we know that the argument for our trig function is going to be this angle here, okay? And just as we use the unit circle to model what our trigonometric functions are going to be like, hyperbolic functions are modeled via the unit hyperbola. And so I'm going to scroll down here and show you what the unit hyperbola looks like in figure 1D, okay? So for figure 1D, notice I've only drawn 1/2 of the unit hyperbola because I actually have another half of it that's on this side here. And if I'm just considering the portion of the unit hyperbola that is in quadrant number 1 here, then notice that if I look at this, I could actually define this this unit hyperbola in terms of what I'm going to call later on cosine hyperbolic and sine hyperbolic functions, okay? Now, notice also here that we have a sector area from, I guess, in between the shape of point O, point P, and point A, or we can say just shape AOP. And it turns out here that the argument for our hyperbolic functions here is a u that's very similar to the u that we were talking about whenever we looked at the sector area using the regular trigonometric functions. Okay, so make a long story short here, if we were considering the same angle theta that would go from the positive x-axis to this ray where points O and P go through, that sector area there is also going to be equal to u divided by 2, okay? Or put another way, we know that the this argument u here is actually twice the sector area that we see in here. So that relationship of sector area and circular angle that we're used to seeing, that roughly holds with the hyperbolas. So I'm saying all this to say that whenever we deal with hyperbolic functions, the main thing that I want you to know here is that the argument for a hyperbolic function is not necessarily an angle, okay? It's more so talking about the sector area that is created by the angle created in that sector, in that shape AOP, okay? So it is not an angle just like how it is with trig functions, but it is indirectly related to the angle in that you're actually referring to the sector area, okay? Now, how it's similar to trig functions here is that whenever we are dealing with the unit circle, we see that the actual sector, we see that this value u here is actually the same thing as the arc length, which is the same as the angle. And all that just so happens to work because, again, we're working with the unit circle there. But again, when we look at an hyperbola, a hyperbola rather, we see that there is not a direct relationship to the angle and the argument for the hyperbolic functions here. And so, again, we just got to remember that whenever we put those arguments in for cosine hyperbolic and sine hyperbolic, like how you see me having here, that those are actually referring to sector areas, okay? So that's the main thing that I want to get across there. Now, with that being said, we're now going to establish what hyperbolic functions actually are. And so in short, what they really are is just very convenient linear combinations of the functions e to the x and e to the minus x that tends to pop up a lot in a lot of applications, especially engineering applications. So we see it so much that we're like, hey, we need to find a simpler way to be able to express these packages of functions that have this linear combination of e to the x and e to the minus x in it. So it's more efficient to deal with. And so that's what we're going to talk about next, is actually establishing what this sine hyperbolic and cosine hyperbolic, what those functions actually are. So to establish these two functions, let's consider this function f, which is just 1/2 times e to the u minus e to the minus u, and this other function g, which is same thing, but we just have a plus here instead of a minus. Now, it turns out that for the unit hyperbola, that if we were to allow x in this formula for the unit hyperbola, if we allow that to be the same thing as g of u, and if we allowed y here to be the same as this function f here, then when we plug this into the unit hyperbola formula, you'll see that once we do that and we do all the manipulation there, what we end up with is that these two functions actually satisfy this equation here, okay? And of course, you see all the work that I've done there to make that happen. So in short, remember that we're trying to model these functions to be very close in concept-wise to a trigonometric function. And if you remember, we have cosine squared of theta plus sine squared of theta is equal to 1, and that mimics the unit circle, okay? So we see here that for the unit hyperbola, if we have this function here and this function here, it's actually going to give us a similar result. So just like how we parametrically define this unit circle with cosine and sine, we're going to parametrically define the unit hyperbola in terms of a function that we're going to coin as functions that we're going to coin as the hyperbolic cosine and a hyperbolic sine, okay? And so here we're going to take what's on the inside of this and call this cosine hyperbolic, or the hyperbolic cosine, you can call it that. And we're going to call this sine hyperbolic, or the hyperbolic sine function. And so again, all we're doing there is just saying that, hey, we see that these two linear combinations of e, to some variable plus or minus e to the minus of that variable is kind of playing the same role as a cosine theta and sine theta functions do with the unit circle. So it's convenient for us to rename them that way, okay? So because of that, we're going to let sine hyperbolic of u, which we also call sinh u for short, just to be e to the u minus e to the minus u, all that divided by 2. And we're going to let cosine hyperbolic of u, also referred to as cosh u, is going to be e to the u plus e to the minus u, all that divided by 2, okay? So now that we have that established, the next thing that we want to see is, hey, if sine hyperbolic and cosine hyperbolic are sort of playing the same role as cosine and sine do with the trig functions, well, what happens if I try to combine, different variations of sine and cosine, just like how sine and cosine hyperbolic, just like how I would with regular sine and cosine functions, to see if I can come up with some identities that would be similar to the trigonometric identities that we're used to. Well, it turns out that we can actually do that. And when we do, we're going to see that we have identities that are going to be very similar to, but not exactly the same as our trigonometric identities that we're used to dealing with. And so we're now going to talk about establishing those. So we see that if we take the same approach as we would in trying to figure out what tangent of some angle, cosecant, secant, and cotangent of some angle is in trigonometry, if we do the same thing with these hyperbolic functions, then we see that a tangent hyperbolic of u is just going to be sinh u over cosh u. And of course, if we write both of those, we see that the 1/2 here, and both numerator and denominator would reduce to 1. And so we see that tangent hyperbolic is really just the difference of e to the u and e to the minus u divided by the sum of e to the u and e to the minus u, okay? Now, of course, we know that if cotangent is the reciprocal of tangent, then that means that cotangent hyperbolic is going to be the reciprocal of tangent hyperbolic. So we see that if we just flip tangent hyperbolic, we will have cotangent hyperbolic, okay? So we also see here that if we take the reciprocal of sine hyperbolic, we're going to get cosecant hyperbolic. which is essentially just sine hyperbolic of u flipped. And same thing with secant hyperbolic is just going to be the reciprocal of cosine hyperbolic. So just like we did for the trig functions, if you just remember what sine and cosine of an angle are, you could form all the rest of the basic trig functions just knowing that. And we do the same thing with these hyperbolic functions. So next, just like how we would if we were studying trigonometric functions, after we establish what they basically are, we would want to know what the graphs of these functions look like. And so we're going to do the same thing with these hyperbolic functions. We need to get an idea of what these graphs are like so that we can know the behavior of them. And this will also intuitively tell us things about the derivative of these types of functions, as well as the antiderivative of these type of functions. And so I'm going to go ahead and move on here. So these are what our basic graphs of hyperbolic sine, hyperbolic cosine, hyperbolic tangent, and hyperbolic cotangent are. Okay. Now remember that all these functions are just some type of linear combination or quotient of linear combination of exponential functions e to the x and e to the minus x. Okay. So with that, the point of me bringing that up is that I know most people don't necessarily try to remember what these graphs look like, but it is good to be able to look at these graphs in their exponential form to kind of guess what they might look like. And so we could use first year calculus principles of doing curve sketching, or we could just evaluate the limit of these functions, let's say at their endpoints and at certain values to kind of get an idea of how this function behaves. But in general, these are the graphs. Now, I personally prefer to deal with the graphs versus, trying to remember all the properties of sinh of x and cosh of x and cotangent and tangent hyperbolic of x, just because all the properties that you need to know about these functions are actually communicated on the graph. Okay, so we can see what the domain of each of these functions are, what the range of each of these functions are. If there are any discontinuities in the graph of the function, we can see what that is for each one of these functions. We can also see what functions are one-to-one functions and which ones are not. And of course, that's important to us because functions that are one-to-one are very easy for us to find what the inverse function would be for it. And of course, that's important to us here because we will be dealing with inverse hyperbolic functions as well. And we can also see, for instance, like cosh of x, and I'm going to scroll down here a little bit more, sech of x or secant hyperbolic of x. These are the two functions that are not one-to-one. So that means we would have to restrict the domain of these functions to force a portion of that function to be one-to-one and just come up with an inverse function for that. Okay, and of course we'll see that sort of thing later here. Again, the main thing I'm wanting to do here is to make sure that hey, there are graphs for these functions, and if you can either remember or at least reference the graphs of these functions, then you're doing very good on remembering the basic properties of these functions. So the next thing I want to talk about is just stating all of the corresponding identities that go along with these functions now that we've established what they actually are and we've seen graphs of them. And so here are some of the identities that we would have for these functions here. And if you notice, they look very similar, not exactly the same, but very similar to our trigonometric or some of the trigonometric identities that we have. So for instance here, for our hyperbolic function, this one is our fundamental identity. And this one just basically models that the unit hyperbola. Of course, if I was to take the unit hyperbola in its parametric form like this and divide it by cosh squared of x on both sides, and then divide it by sinh x of both sides, then I would get these corresponding identities here. And so that works the same way if for trig, if I had sine squared plus cosine squared is equal to 1, and let's say I divided both sides by sine squared, then I know sine squared divided by itself is 1. Cosine squared over sine squared is going to be cotangent squared. And of course, 1 over sine squared is going to be cosecant squared. Okay. And so my point in doing all of this is to say we can do the same sort of thing with this particular function here. So let's say if I said cosine hyperbolic minus sine hyperbolic is 1. If I divide both sides by sine hyperbolic, then here I'm going to get cotangent hyperbolic squared minus 1, which is going to be cosecant hyperbolic squared. Okay. And of course, when I divide both sides by sine hyperbolic squared, it eventually refers to this identity down here if I was to rearrange this particular equation to solve for cosine hyperbolic squared. Okay. So my point here is that, again, if you remember your basic trigonometric identities, you could kind of leverage that to be able to remember these, although there are some differences. So for instance, for here, if you remember that for our regular trig identities here, that cosine of 2x is the same as cosine squared of x minus sine squared of x. And of course, that can also be written as 1 minus 2 sine squared of x, also can be written as 2 cosine squared of x minus 1. Okay, so those are the 3 different ways we can write cosine of 2x. Well, we can use something similar to that to help us to be able to, first of all, remember what cosine of 2x is. And since, of course, this is minus here, then that means that's going to be plus there whenever we do the cosine hyperbolic of 2x. But then we can use this relationship along with this equation here to be able to rewrite cosh of 2x in different ways. Okay. And so in doing that, one of the things that helps us do is be able to come up with these reduction formulas as well. Okay. Now, for those of you that may be interested in, well, all right, how do I start with something simple like this fundamental identity for the hyperbolic functions, and how do I actually prove the rest of these? And so to do that, you would start off, of course, by proving this one, and you could use essentially just this particular equation here and what you know your sinh and cosh functions to be to actually figure that out. So you could start here and do that, just writing it in exponential form, and then you can kind of back your way into proving that. Once you have these two, then you can use these two identities to actually establish this one. Takes a little while, but you can do it. And then, of course, from there, once you have that, the rest of these come very easy, okay? And there are many more than these. These are just the basic ones that we use most often when we use these types of functions. All right, so let's move on. Now, one thing I want to remind you of here is that with some of our trig functions, we know that they can be periodic. But we know that with the hyperbolic functions, none of them are periodic, okay? So because of that, we know that we're not going to have, let's say in trig, we would have properties or identities that go along with those functions based upon the fact that they are periodic, we're not going to have any of those identities with the hyperbolic functions. And so that's one way that the hyperbolic functions delineate themselves from the basic trigonometric functions. Okay. Now, again, I mentioned this before as well, that because these functions are not periodic, it makes it kind of easy for us to tell which ones are one-to-one and which ones are not one-to-one. And of course, the ones that are not one-to-one, meaning that they, in its natural form, do not have an inverse function, we have to restrict the domain so that we can force one to happen. So here, if we did not have the graphs of these functions, then we would have to memorize all this stuff here for each of these functions. And so my point is that it's probably easier to memorize the graph and look at that versus trying to remember all the stuff that's in this chart here. So again, it's up to you how you want to do it. Most people, we just reference these because these functions are not used as much as basic trigonometric functions. But if you have to remember this stuff, then my suggestion is that you try to memorize the graphs first, because by doing that, you automatically have all this information here. All right, so now that we've established what hyperbolic functions are, what their graphs look like, we can now start talking about dealing with these types of functions in a calculus sense. And of course, in calculus, one of the main things that we do is we want to figure out what's the instantaneous rate of change of functions like this, as well as what's going to be the integral. And of course, one way that we could interpret that is really not the only way, but it's just one way, is area under the curve of those functions. Okay, we do have a more general interpretation, but for sake of simplicity, I'm just going to use that for now. So if we recall here that cosine hyperbolic is just 1/2 times the sum of e to the u and e to the minus u, and sine hyperbolic is going to be the same thing, but the difference of e to the u and e to the minus u. If we were to differentiate these functions here in their exponential form, what we would see here is that cosine hyperbolic, when we take the derivative of that, is just going to be sine hyperbolic. Okay, and just notice here for clarity, I'm actually putting this extra du over dx here because I'm assuming that this argument u here may actually be a function in and of itself. So I'm applying the chain rule to each of these derivatives that I'm stating. Okay. All right. So if we take the derivative of sinh u, we'll see that we just get cosh u. Okay. So the derivative of sine hyperbolic is cosine hyperbolic. The derivative of cosine hyperbolic is sine hyperbolic. Notice here that we don't have the whole sign change thing that happens whenever we deal with the trig functions. Because, for instance, we know that for a regular cosine function, if we took the derivative of that, that would be minus sine. Okay, so we don't see that sort of thing happening with the hyperbolic functions, which makes it a little bit easier for us to remember the derivatives of sinh and cosh. So just like how we would do in with normal trigonometric functions, now that we know the derivatives of cosh u and sinh u, we could use the quotient rule to be able to figure out what the derivatives of tangent hyperbolic, cosecant hyperbolic, secant hyperbolic, and cotangent hyperbolic would all be. And so I'm not going to bore you with the details on that. Just know that if we were to actually form those functions and did the quotient rule to it, then we would get these outcomes here. So we know that tangent hyperbolic, the derivative of that is secant squared hyperbolic. And that sort of mimics what we know with regular trigonometry, because we know the derivative of tangent is also secant squared. Okay. the derivative of cotangent hyperbolic is going to be a negative cosecant squared hyperbolic. And again, that mimics the same thing that we see with regular trig functions. Here we see that with secant hyperbolic, this is a little different because we know that in regular trig, the derivative of secant of some angle is going to be secant times tangent. Whereas here, secant hyperbolic, its derivative is negative secant hyperbolic times tangent hyperbolic. Okay? And then, of course, we see here that cosecant hyperbolic, its derivative is going to be negative cosecant hyperbolic times cotangent hyperbolic. And that's pretty much the same, okay, as it is for regular, whenever we take the derivative of cosecant with regular trig functions. So if we know the derivatives of certain hyperbolic functions, then that means that we also know the corresponding antiderivatives for them, okay? So since the derivative of cosine hyperbolic is sine hyperbolic, we now know that the antiderivative of sine hyperbolic is cosine hyperbolic, okay? Similarly, we know that the derivative of tangent hyperbolic is secant squared hyperbolic, so that means that the antiderivative of secant squared hyperbolic is tangent hyperbolic. And so if we follow suit with the other basic derivatives that we know for our hyperbolic functions, we can actually form antiderivatives of the rest of these functions that are listed here, okay? So again, if you know the derivatives, you can kind of figure out what the antiderivatives are, okay? Now, for inverse hyperbolic functions, if you recall, when we looked at the graphs, we had basically all the functions that we would consider to be odd, they would be one-to-one functions. And I'm using that word odd loosely because of the fact that we know that when dealing with regular trig functions, we know that all the functions except for cosine and secant were odd functions, okay? So just like how trig functions have their corresponding inverse functions, our hyperbolic functions also have inverse functions. And of course, to establish those from a graphical standpoint, if the original hyperbolic function is not one-to-one, like a cosh u or a sech u function, we would have to restrict the domain for those, okay, and then form a function out of that. Now, it turns out that since all these functions are really composed of exponential functions, e to the x and e to the minus x, then that means since we know that the inverse function of e to the x is natural log of x, there should be some way for us to rewrite all of these hyperbolic functions in terms of natural log of something, okay? And it turns out that there actually is a way for us to do that. Establishing it, it's not terribly difficult, but it does take a little while to do it. But we do have a way of doing that. And so rewriting the inverse hyperbolic functions as logarithms is very useful because of the fact that, number one, you're not going to see buttons on a calculator for most calculators that are going to calculate inverse hyperbolic functions, okay? But you do have a natural logarithm button on any scientific or graphing calculator that you use. So if you can know what the inverse trig function identity is in logarithm form, then you can pretty much calculate inverse hyperbolic functions for anything that you need, okay? So these are the graphs of our corresponding the hyperbolic functions and their corresponding inverse functions. So the graph that you see here that is in yellow, that would be your original hyperbolic function. The graph that you see in the bluish green, type of color, that would be your corresponding inverse function. Okay. And so you see here that following the definition of an inverse function from a graphical standpoint, our inverse functions for the hyperbolic functions that we have are just reflections about the original function about the line y equals x. Okay. And so you see that for the sine hyperbolic, that's the case. You see here for the cosine hyperbolic, we restricted the domain of cosh of x to be greater than or equal to 0 so that we can have this piece here, and thus we can take that portion that's 1-to-1 reflected about the line y equals x and come up with this function here. Okay, and of course you kind of see the others on how they work. Now notice that for our inverse tangent hyperbolic, our cotangent inverse hyperbolic, and our cosecant inverse hyperbolic, that all those functions, just the inverse function is shown. We don't actually have the graph here of the original function as well. For the tangent hyperbolic function and its corresponding inverse, since tangent hyperbolic is 1-to-1, it's very easy to just flip the graph of tangent hyperbolic to come up with its inverse. Same kind of thing with the cosecant hyperbolic, and that one looks very similar as well. Of course, with the cotangent hyperbolic, that one's also one where if we just flip the graph, we could come up with the inverse function for that. So just letting you know that the only ones that are actually a little bit tricky are the cosine hyperbolic inverse and the secant hyperbolic inverse because of the fact that you have to restrict the domain. All right, so now that we are talking about inverse hyperbolic functions, then of course we need to talk about the derivatives and integrals of these particular functions as well, or basic antiderivatives for this function as well, for these types of functions as well, I should say. So I'm not going to go into a whole lot of detail on these, other than the fact that the same way we would establish these differentiation rules here are the same way that we would establish them if we were trying to establish the derivatives of the inverse trig functions. And of course, we would do that by using implicit differentiation. So the same technique is used to come up with all of these differentiation rules for these inverse hyperbolic functions. And thus, if we know what the derivatives of these inverse hyperbolic functions are, then we also know what the corresponding integrals or most general antiderivatives could be as well. Okay, and so again, just want to state those. We'll use them. I know that in the last video in this series, I'm actually going to go through and show you how we establish some of these derivatives here by using implicit differentiation, just in case you're interested in seeing that. And so just like how we have in regular trigonometry, we do have some identities for inverse trig functions. We do have the same sort of thing for inverse hyperbolic functions. And so we see here that the inverse of secant hyperbolic is going to be the same as the inverse of cosine hyperbolic, but the argument is just going to be 1/x. Okay, and of course, sine hyperbolic and cosecant hyperbolic, those inverse functions have the same relationship, and cotangent hyperbolic and tangent hyperbolic, their inverse functions both have the same relationship as this one. So basically, secant inverse hyperbolic and cosine inverse hyperbolic go together. sine hyperbolic and cosecant hyperbolic inverse go together, and cotangent hyperbolic and tangent hyperbolic inverse all go together. Okay. So now, if you recall, we did say that we should be able to take our inverse hyperbolic functions and rewrite them as logarithms. And so I'm just going to state these. I'm not going to go through the process of actually establishing them. Now, of course, there are some videos that you can find out on the web that will show you that. I know I actually plan on making one or two of those myself, just to show you how to do it if you're interested in doing that. But as for now, the only thing that we really need to know is what these are, okay? And I know that one of the ways that these types of functions are used, I know in analog filter design, if we are designing like, let's say Chebyshev filters, or if we're doing stuff like Chebyshev filters, you'll see this kind of stuff pop up, okay? Some Butterworths, but mainly Chebyshevs and inverse Chebyshev filters. You'll see this kind of stuff, pop up a lot in the process of being able to design those types of filters if you're an electrical engineer. So that's one of the ways that I know personally that I've used these functions a lot in some of the things I've done outside of teaching mathematics. So at this point, I'm going to go ahead and end this video since we've talked about all the basic things that we need to talk about as far as establishing what basic hyperbolic functions are, their derivatives, their integrals, basic graphs. So we've done all that. So in the next video that I'm going to do, I will start with some of the examples that we would normally work in trying to get fluent with working with these types of functions. So I'll see you in that next video.